Okay, so this is the final example for the gravitation material, kind of a fun example, with a slightly counterintuitive application of some of the theory we've been using. So let's read what it says. The sun, which is 2.2 times 10 to the 20 meters from the galactic center, revolves around that center every 2.5 times 10 to the 8 years. That's a quarter of a billion years for us to orbit the center of the galaxy. Assuming every star in the galaxy has the same mass as the sun, which is 2 times 10 to the 30 kilograms, that the stars are distributed uniformly in a sphere about the galactic center, and that the sun is at the edge of that sphere, estimate the number of stars in the galaxy. So, as I say, we're making some huge assumptions here. So we're told to assume that every star in the galaxy has the same mass. That's the first assumption. That they're distributed uniformly in a sphere. That's the second assumption. And that the sun is at the edge of that sphere. That's the third assumption. And we're asked to estimate the number of stars in the galaxy. And as we'll see, what this comes down to is calculating the mass of the galaxy based on these two assumptions, and then calculating the number based on this one. So we're given three numbers. We're told the radius of the sun's orbit, which we're going to assume is circular. We're told that it revolves around the galactic center every 2.5 times 10 to the 8 years. That's the second number. And the third number here is the mass. So we're going to use all of these in a different way. First of all, let's see how these assumptions kind of allow us to solve the problem. So we're told to assume that all the stars are distributed uniformly in a sphere. Okay, and that this is this kind of center of the galaxy. So that's the middle point there. And we don't have to assume necessarily that there's anything there. I mean, if you've been paying attention to any of the news over the last while, in fact, if you're watching this in 2026, then just this week, there's a hypothesis that the center of the galaxy has a big lump of dark matter at the middle of it, whereas previously people thought that it was a supermassive black hole. But if we assume that all of the mass is distributed uniformly in a sphere, so basically we've got a big kind of lump of mass, but that the stars are all sort of spread out throughout this sphere, then what that means is that we can treat all of the mass of the galaxy as being concentrated at this point. And that's the same way that we kind of treat the sun as a kind of like a point in space. We've got the Earth going around the sun. Even though this is a massive object, because it's spherical, we assume without any loss of accuracy that all of the mass is concentrated at the center. So for our assumptions here, we're assuming that all of the mass can be modeled as sitting at the center, even though that's not the case. Okay, we know that it's uniformly distributed, but this is the center of mass of the galaxy, and therefore we kind of assume that everything's sitting there. So what this problem amounts to then, the other assumption then is that the sun is on the edge of that. And that's important because for planets that are in here somewhere, so if I choose for stars that are in here somewhere, if I choose some other point here, the gravitational attraction of all of the other stars around about it, the ones that are outside, it all kind of cancels out. So that it's being pulled towards the center, but it's also being pulled away from the center by the stars that it sees out there. So this would experience a lower gravitational pull, whereas the sun, which we are assuming to be on the edge of this sphere, it will experience the full force of gravity due to the mass of the galaxy. So those are the two assumptions, that we've got everything distributed uniformly in this sphere and that the sun is at the edge. Okay, so we're going to use those two assumptions then to reduce this entire problem down to thinking about the sun being here, the center being there, and using the kind of parameters of the orbit. Okay, so the sun is orbiting around this center in some circular orbit, to calculate the force, or rather to use the force to calculate the mass of this center. That's how the assumptions work. So let's see how this comes out in the numbers. So we're going to apply Kepler's third law. So I'll just write that as K3 like that to find the mass. So Kepler's third law, which we wrote down in the class, was T squared is equal to 2 pi all squared over gm times r cubed. So this is NASA Kepler's law. Kepler's law is that the square of the time period is proportional to the cube of the semi-major axis of the orbit. But what we showed in the class is that using Newton's gravitational law, we can actually assign a value to to that constant. And for circular orbits, we replace the semi-major axis with the radius of that circle. Okay, so this is the formula that we wrote down in class, and we can simply rearrange that to make m here the subject of the formula. Okay, so m here is the mass of the galaxy, and when we rearrange the formula, we'll get that m is equal to 4 pi squared or cubed over gt squared, rather. Okay. Now, we need to convert some units because the time here is given to us in terms of years. G here is Newton's gravitational constant, okay, which is 6.67 times 10 to the minus 11. This time period here is, where are we? There's the time, it's 2.5 times 10 to the 8 years, which, as it turns out, if you do the conversion, is 7.88 times 10 to the 15 seconds. R here is the radius of the orbit of the sun, which we're told in the question is 2.2 times 10 to the 20 meters. And pi obviously is just a constant. So we can substitute in all those numbers and calculate what the mass of the galaxy is, and it comes out to be 1.01 times 10 to the 41 kilograms. Okay, so again, we've used our assumptions to model this entire problem with all of the stars in the galaxy and the sun moving around it as 2 point masses, the sun at the in the circular orbit and the galactic center, which is the center of mass of all of the mass of the stars. Okay, so we calculated the mass of the galaxy. What we're asked to calculate is the number of stars in the galaxy. So if we know the mass of the galaxy, and we assume that all of the mass is in the form of stars, which it isn't, but as we'll see, this is just a rough calculation, so it's fine. So if we know the mass, and we know the mass of one of the stars, which is our first assumption, then we can calculate the number of stars. So the number of stars is given by dividing the mass of the galaxy by the mass of the sun. And when we put in the numbers then, so this is the 1.01 times 10 to the 41 kilograms that we just estimated. And the mass of the sun was 2.0 times 10 to the 30 kilograms. So obviously the units cancel out here, which is important because we're calculating a number, so that doesn't have any units. And this comes out to be 5 times 10 to the 10 stars. That's our estimate. Now, 5 times 10 to the 10, that's 50 billion stars. That's the estimate that we've come up with there. The actual number is 100 to 400 billion. That's the current estimate for the number of stars in the galaxy. So we've made some fairly drastic assumptions, but we still come out with something which isn't too bad. All right, we're out by a factor of 2. Which, given the kind of severity of those assumptions, isn't too bad. And this kind of calculation is very common. This is what physicists call a back of the envelope calculation, where you just make a whole bunch of approximations and see what comes out. But this part is the really important part in terms of how these assumptions lead us to being able to model this whole thing as 2 point charges, 2 point masses, and then use Newton's gravitational law, which is Kepler's third law in different form, to solve this problem.